On a problem like this, you always draw free body diagrams. I recommend not scribbling around on this or drawing these microscopic little diagrams. Draw something big because you've got a lot of information that you need to fill in there. So here's the tension. It points up the ramp. Here's the normal force, and let's just label these 1 and 2 for now. Don't put the numbers in until the very last step. That's the normal force on 1. There is friction between the 50 kilogram block and no friction. I'll just jot that on there, no friction on there. This is object number 1. And we've got M1G pointing down. Okay, so there's the free body diagram. And whenever we have an inclined plane problem, what we like to do is to tilt our coordinates because it makes everything so much easier. It makes the math a lot easier. So instead of the usual x and y, we're going to make these kind of coordinates, which means the only vector we have to break into components is the weight vector. It has this and this. This is the angle of the inclined plane. How do I know that? Because I've done this problem a whole bunch of times, and that should be the same reason that you know it too. No need to derive any fancy geometry. The way I like to remember it is that this angle is the one that would be 0 if this normal force were straight up. So just picture this big line here turning into just straight up and down, and so that's the angle of your incline. So this is M1G cosine of whatever that angle is. This is M1G times the sine of whatever that angle is. Okay, so that's just the free body diagram for number 1, and let's keep working with this. The sum of all of those forces acting on that free body diagram add up to 0. How do I know that? It says these blocks remain at rest. Okay, so that was another thing. If you know that those forces add up to 0, then you were doing pretty well. That means that N1 plus T plus M1G, everything added up as vectors, equals 0. I saw a lot of people doing math here, putting the M1G over here with the vector sign and putting a minus. Don't do math on this. All you're doing with this is breaking it into components. You're not doing math on it. You're not doing algebra and putting the n over here or anything like that. So the x component for that equation is going to be t, which points in the positive x direction. M1G points in the negative x direction. And remember, these are our new x and y directions. And the sum is equal to 0. Okay, so I just checked each one of these vectors for which way it points and if it has a value other than 0. Normal force is perpendicular to x, so it has a value of 0. T points up the ramp. M1G sine theta, just that component, this is a right angle, that points down the ramp in our negative x direction. Okay, so here's one piece of information that allows you to solve the problem. We're going to do the exact same steps for the other block. It's a little bit more complicated here because there's friction. So let me make some room, and we're going to do the same process for number 2. So block number 2 has a free body diagram that looks like this. It has tension that points up the ramp. It has a normal force perpendicular to the ramp. It has friction. I don't know which way it points. I'm just going to draw it in here. If it turns out that my coefficient of friction comes out to be negative, so say you do out all the math and it comes out to be negative, that meant that your coefficient of friction would have pointed the other way. And that's okay. It's not a big deal that you do that. It's basically what a negative would mean for this particular problem. And then, of course, we have the weight. We have to do the same thing again. We can use the tilted set of coordinates. We can have, this is our y direction, this is our x direction, which means that now we break down this weight into components. This is perpendicular. This is this angle right here. And we know that because if n pointed straight up, this angle would go to 0. N pointing straight up means the inclined plane is flat. And we do the same thing again. We say the tension plus the normal force plus M2G plus the friction force all add up as vectors to 0. I know that because Newton's laws tell me that the sum of the forces here are 0. The blocks remain at rest. That means this. This means that you add up all of the 4 vectors here. So if you do the y component, then the y component of that, then you get the tension minus the friction force minus m1g, sine of your angle there, equals 0. You can do the x component also. You're going to need to do the x component here. We didn't need to do it on the other one, but here we definitely do, because our friction force is equal to mu n. And then our normal force comes from the fact that this is our n2. So the normal force, here we're looking at the x components. The x components tell us that the normal force minus this component here, which is m2g cosine theta. Equals 0. So here we put this here, we put this in for this f. Let me just write on here. M2g cosine theta, and this one is M2g sine theta, where theta is this angle right here. Okay, so now we've got enough information, we can finish and solve the problem. Again, you didn't have to know that friction points down the ramp. If you pointed it up the ramp, that's fine. Like if you thought maybe this thing would slide down the ramp and friction keeps that from happening, then what would happen is that you would get the same mu just with a minus sign in front of it, which is not a big deal. It would just tell you that you picked the wrong direction for your friction force. Okay, so you go through and now you've got enough information that you can solve the problem.